Okay, fine. So let's start. So today we'll be dealing with interpretation of ABG. Yesterday we dealt with the physiology of normal acid-base balance, how it is maintained in our body, and the buffer systems. Today we'll start with ABG. And for the purpose of interpretation, there are different approaches. There are different approaches that is being followed. Okay. And today what we are going to read is the nothing but traditional approach or Boston approach. It's called as traditional approach or Boston approach. Okay. This is nothing but based on the Henderson-Hasselbalch equation, which we'll see now. And it was mainly given by Schwartz and Reilman. As we see in the picture, we see Arnold Reilman, and this was given by Schwartz and Reilman. It is called as the traditional approach or Boston approach. And then there is one more approach which is called as Copenhagen approach. These two came at the same time. It came around 1960s. These two were present, and each of them debated with each other, claiming themselves to be superior. But then, yeah, both approaches give you almost the similar values. When we are following traditional approach, we are following the traditional approach, and this was given by Sigard and Astor. It was based on something called as base excess, nothing but the value, normal base excess value. You don't have to know this, -2 to +2. If greater than +2, it is metabolic alkalosis. Less than -2, if it is less than -2, that means there is metabolic acidosis. That's all. That was the basic concept of base excess. You guys don't have to know the whole concept. Then came Stewart approach. This came around somewhere around 1980s. Something called as Stewart approach by Dr. Peter A. Stewart. He claimed that other than the HCO3 minus, we mainly concentrate on HCO3 minus values to control the pH. But there are other values as well. Control the pH by H plus ion concentration. So mainly it deals with H plus and HCO3 minus. These previous two approaches, but other ions like Na plus, K plus, Cl minus, etc., they as well influence the pH. So he got into effect these values as well. He took into effect these values as well into his approach. Okay, and he called it something as strong ion difference and all. No need to not be dealing with it. We no need to deal with it because we'll use the traditional approach or the Boston approach. So to start the way, this is mainly based on Henderson-Hasselbalch equation. So it takes into account HCO3 minus as the central value. HCO3 minus as the central value. The Boston approach takes into account HCO3 minus as the central value, leading to change in pH. Okay, using this equation, Henderson-Hasselbalch equation. What is this equation? pH equals the dissociation constant, characteristic for every buffer system, which we read yesterday, pK plus log undissociated by associated form. So log HCO3 minus by 0.03 into PCO2. This is nothing but associated form of HCO3 minus CO2. By Henry's law, we get this equation. Okay. So normal pH will be what? Normal pH will be 6.1 for if we take into account bicarbonate system by log 24 normal concentration of HCO3 minus divided by 0.03 into PCO2 normal is 40. So we get pH of around 7.4 by using this value. So now coming to the pathological states which can disturb this value. To disturb this value, 4 pathological states are possible: metabolic acidosis and alkalosis, respiratory acidosis and alkalosis, which changes the pH. Okay, these are the 4 basic disturbances which leads to change in the above pH value. Next, we see that in this equation, in this Henderson-Hasselbalch equation, we can see that all the 3 values are interrelated. If there is change in one value, all the other values change. But the aim of our system is to keep the pH normal. Keep the pH normal. So change in one of the values, that is if there is change in HCO3 minus, there should be change in PCO2 as well to keep the pH normal. So since they are interdependent, if this changes, this as well needs to change to keep the pH normal. That is how the buffer system works. That is the aim of buffer. So that is where the second concept of compensation comes into picture. What is compensation? Nothing but if there is change in HCO3 minus, like we say HCO3 minus increases, then the body compensates by increasing PCO2 as well to keep the pH normal. How does compensation take place? That was part of normal acid-base physiology, which was there, which we spoke about in detail yesterday. So the 4 basic disturbances are what we saw now. First is we'll take metabolic acidosis. If there is metabolic acidosis, what happens in the body? There will be decrease in HCO3 minus levels. If there is decrease in HCO3 minus level, there will be body compensates by decreasing PCO2. HCO3 minus level decreases, body compensates by decreasing PCO2 so that pH becomes normal. How does PCO2 decrease? By increasing respiratory ventilation. If there is increase in respiratory rate, PCO2 will decrease because dissolved CO2 in the blood decreases. So PCO2 decreases. How 0.03 came? That is, again, you'll have to derive it. There's an equation for that. We don't have to deal with it. It is not that important for us, Ayush. Similarly, there is metabolic alkalosis. If there is metabolic alkalosis, there is increase in HCO3 minus levels. If there is increase in HCO3 minus levels, body again compensates by increasing PCO2. Okay. See this one. If there is increase in HCO3 minus levels, body increases PCO2. How does it increase PCO2? Respiratory rate. It just decreases the respiratory rate. If respiratory rate decreases, dissolved CO2 automatically increases. So there will be increase in PCO2. Similarly, coming to respiratory acidosis and alkalosis. In respiratory acidosis, there will be increase in PCO2. If there is increase in PCO2, that is the initial abnormality, body has to, if this increases, HCO3 body increases HCO3. How kidneys come into play? It increases the reabsorption of HCO3 minus and H plus excretion. That's all, simple. Similarly, respiratory alkalosis, if there is decrease in PCO2, there will be decrease in HCO3 minus levels as well. How? By decreasing the reabsorption. That's all. The simple concept is there will be a disturbance in the body which will dysregulate this equation, then which is because of the abnormality caused. Then body compensates to bring back the pH to normal using one of the mechanisms. So that was the whole concept behind this. Okay. So how do we do so now coming to ABG, how do we do ABG? What is the use of ABG? To detect these abnormalities, we do ABG. To detect these abnormalities, to diagnose what the disturbance is, we do ABG. What is the procedure? First, we'll have to draw the blood. How do we draw? We draw arterial blood. It is arterial blood gas analysis, not venous. So we have to draw arterial blood. How? First choice is radial artery. If radial artery is not fine, then we go to femoral artery. Femoral artery is hardly used. We usually do it through radial artery. And if we have put an intra-arterial line, then we can directly draw the blood. Usually brachial artery is used. First, we'll have to do Allen's test. Before the procedure starts, we'll have to do Allen's test to check for the patency. How do we do? We compress both radial and ulnar artery. Yeah, good, Pawan. Good, very good. Once for around 15 to 30 seconds, you compress radial and ulnar artery. Then you leave the ulnar artery. And you look for, since the hand will be pale, once you compress, you look for the hand to become plethoric again, for it to become red again. If ulnar artery is not patent, hand remains pale. So in that case, we don't do through radial artery. Why? Because on doing radial artery as well gets punctured. So radial artery is abnormal now. Even if ulnar artery as well is abnormal, then hand will become ischemic. So that is the reason why we'll have to do Allen's test first. Okay. Followed by drawing the blood. This is followed by drawing the blood. What is the needle we used? 21 gauge in case of adults, 23 gauge in case of pediatrics. We use something called as heparinized needle. Why? The blood shouldn't get clotted. No, since the blood shouldn't get clotted, we use 0.5 ml of 1:1000 dilution of heparin. You draw the heparin, then you flush it out. First, you draw heparin, take it throughout the syringe, and then you flush it out. Okay. You don't keep heparin inside the needle. That's why it is called heparinized needle. Okay. You don't keep it. You flush it out. Once you draw it fully, then you flush it out. Why? Because it causes dilutional effect. Once it causes dilutional effect, you get false values. That is why we don't keep the heparin inside the needle. We just flush it out. Followed by, you put the blood into analyzer. Now, what is important is you either put immediately. If in the ICU setup, you have a ABG over there only, okay, fine. You can put it immediately, or cold chain has to be maintained. Cold chain has to be maintained. And at the earliest possible, we'll have to take it to the biochem lab. Why? Because there will be change in values. If there is change in values, again abnormal readings. Again abnormal readings you get. See, there is drop in the values every 10 minutes, and this drop is much more at room temperature. At 37 degrees Celsius, this drop is much more. That is why you use cold chain. Either you do it immediately in the ICU if there is a ABG machine, or we do it at 4 degrees Celsius. In case the connection goes off, it might take 2 to 3 minutes delay, or there might be a 2 to 3 minutes delay. So you guys don't leave, okay? We'll come back. If that happens, that's been happening, and please don't try sharing the screen. That happens when someone else tries to share the screen. So what are the contraindications for ABG procedure? This was the procedure. What are the contraindications? If there's abnormal Sandwich test, then we don't use the radial artery, we go to some other artery. If there is Raynaud syndrome, again indicating there's a peripheral arterial disease, so we don't do. If there is infection at the local site, again we don't do, in order to avoid spreading infection to the whole body. And in case of severe peripheral vascular disease as well, we don't do. And we should ensure that there is no contact with air. If there is contact with air, again, there will be false values because PO2 will increase and PCO2 decrease due to diffusion of gases. Once we do the procedure, we put it to the machine. ABG analysis machine, we put it to, as we see in this image. Correct, no? So what all this machine is capable of measuring? pH, PCO2, HCO3 minus, PaO2, and O2 saturation. Of these, HCO3 minus and O2 saturation are calculated by the machine itself using certain complex formulas. Okay, using certain complex formulas. So these are indirect values. These are indirect values. This might be an MCQ for you guys. These are indirect values measured by the ABG. But pH, PCO2, and PaO2 are calculated directly. So in order to know about the disorder, we should know what the normal values are in our body. pH is 7.4, 7.35 to 7.45 it can go, but we take it as 7.4, somewhere average. PCO2 as 40 mmHg, HCO3 minus as 24 milliequivalents, and H plus as 40 milliequivalents per liter. Okay, if there is derangement in pH, if there is derangement in the pH, and we saw if there is this is deranged, there will be this derangement in this and this as well because of Anderson-Hasselbalch equation. That will lead to acidosis or alkalosis. Acidosis or alkalosis. So first we'll see the difference between acidemia, alkalemia, and acidosis, alkalosis. Okay, what is acidemia? Is the physiological state of body pH is acidemia. So if there is pH of 7.26, then we call it acidemia. We call it acidemia. Or if the pH is 7.56, we call it alkalemia. But what is acidosis? What is acidosis? Acidosis is nothing but process which tends to drive the pH towards acidemia or alkalemia is acidosis. So the process is acidosis and alkalosis. Acidemia is the what state the body pH is in, that is acidemia. So if there is acidemia, there can be both acidosis and alkalosis. And alkalosis is possible. Acidosis and alkalosis is possible. But the body is in acidemia. That is what they mean to say. See, both process can be occurring at the same time in case of acidosis and alkalosis. How this happens, we'll see. How will this happens, we'll further see in the lecture. Okay. So first we do the procedure. Once we do the procedure, we put it to the analyzer for the machine to analyze. Then we get the values. After this, what is the step? Actually, before this, we should actually check for whether the calculated values by the machine is appropriate or not. How do we do this? There are two methods. One is we measure serum electrolytes. We measure serum electrolytes at the same time. Serum electrolytes will give us the HCO3 minus levels. HCO3 minus levels. Okay. So, and as I mentioned before only, HCO3 minus are not directly measured. It is indirectly measured using this formula by the blood gas analyzer. That's why it's called as CHCO3. Nothing but calculated HCO3 minus. If this calculated HCO3 minus, on comparing with the serum electrolytes values, if they fall in the same range, plus or minus 2 milliequivalents per liter, if they fall in the same range, then it is considered as valid. If not, then we repeat the test. Okay. Or if serum electrolytes levels are not available, if it's not available, then we use this equation. This equation is again derived from Henderson-Hasselbalch equation itself. On putting the HCO3 minus levels, PCO2 minus levels, and H plus levels, it should be equal to 24. If not, again, we should repeat. If yes, then the test is considered to be valid. These are the two methods. And how do we calculate pH will be given. Okay. How do we calculate H plus is using this table. This table is available in the net. Using this table, we calculate for the respective pH. For the respective pH, what is the H plus levels. Okay. So once we saw the validity of the test, so we do the procedure, put it to the blood gas analyzer, then we see that the test is valid. After this, we come to the first step, that is we see the pH. We see the pH and tell whether it is acidemic or alkalemic. Whether either there is acidemia when it is less than 7.35 and there is alkalemia if it is greater than 7.45. After this, what do we do? We see what the primary disorder is. We got to know the state of body's pH. Now we should see whether it is metabolic or respiratory. So to see the primary disorder, we follow this algorithm. Simple. If the change in PCO2 is the same as the change in pH, okay, if pH is reduced, if PCO2 as well reduces, or if pH increases and PCO2 as well increases, if this happens, then the process is metabolic. If PCO2 and pH goes in the opposite direction, then we call it respiratory. So this is the simple process. So we can take an example. So we have the first example. What is it? What is the primary disorder over here? What is the primary disorder over here? Example 1. pH is 7.34, PCO2 36, HCO3 minus 20. Okay. Shavanti says it's metabolic acidosis. Why? Why is it metabolic acidosis? Because both are moving in the same direction. There is decrease in pH. There is decrease in PCO2 as well. That means there is metabolic acidosis. So good. There is metabolic acidosis over here. Someone asked why there is metabolic acidosis, why it is called metabolic acidosis. Simple. See, firstly, what we see PCO2 value and HCO3 minus value. Okay. If HCO3 minus values are decreased, and PC means the process is metabolic. Okay. We see HCO3 minus levels and PCO2 minus levels. This as well is decreased. And then we check for pH. If pH is decreased, it means there is acidosis. Since it is because of decrease in HCO3 minus, it is metabolic. And PCO2 is compensatory. If we take everything into picture, then we derive at this algorithm. This is just a simplified process to look into it. Okay. So there is metabolic acidosis. So now let's move on. After this, what do we do? We check for compensation. As we initially read, there will be initial abnormality. If that abnormality, to keep the pH in normal, body tries to compensate. Okay, body tries to compensate. How does this happen? This compensation, to see whether there is adequate compensation or not, we use a set of formulas. And what I've marked in blue are the ones which is regularly followed and the ones that is easy to remember. In metabolic acidosis, what happens? Initial abnormality is decrease in HCO3 minus. Levels. To compensate, PCO2 as well decreases, which leads to decrease in pH. Okay. So either using Winter's formula and something else is this simplified approach. We can come to a diagnosis as to whether it is compensated or not. So what is it? If HCO3 minus levels decreases by 1 milliequivalent per liter, then PCO2 should decrease by 1.25 mmHg. PCO2 should decrease by 1.25 mmHg. Similarly, in wherein HCO3 minus levels will be increased, and as a compensation, PSCO2 should increase. So, if HCO3 minus level increases by 1 milliequivalent, then PSCO2 should increase by 0.75 mmHg. That is the compensation. That is how we calculate compensation. Similarly, in respiratory alkalosis, depending on whether it is acute or chronic, respiratory alkalosis, what happens? PCO2 will decrease. This is the primary process. If PCO2 decreases, HCO2 minus as well decreases. Correct, no? So, for every 10 mmHg decrease in PCO2, for every 10 mmHg decrease in PCO2, HCO2 minus should decrease by 2 if it is acute, or it should decrease by 4 if it is chronic. Similarly, in respiratory acidosis, PCO2 will be high. So what will the body do? It will compensate by increasing HCO3 minus. So for every 10 mmHg increase in PCO2, HCO3 minus level rises by 1. It increases by 1. If it is chronic, it increases by 4. That is how we calculate for compensation. Okay. So you guys can capture this image. You guys can capture this image to do further sums. You can take a screenshot or something. So hope you guys took. Now let's move on. Depending on this, either two things can happen. Either it can be compensated or it can be non-compensated. If it is non-compensated, then there is some other secondary disorder as well that is not letting the body to compensate. So there will be one other disorder as well along with the primary disorder. So we'll get mixed picture, mixed acid-base disorder will be there. If it is compensated, then it is called as simple acid-base disorder. Okay. Now, since the sums are not the same as previous times, we've changed the values. So you can't look into the previous times one. Please do this sum. Example number 4. Example number 4. Can you guys do this? Answer, please. Okay. Metabolic acidosis. Sanjay, you tell metabolic acidosis, but what, whether it is compensated or is there any mixed disorder? Okay. Shravanti tells it is compensated. Compensated means simple. Yes, very good. Why? First we see, look at pH. pH is reduced. That means there is acidemia. Then we look at PCO2. Both pH and PCO2 is reduced. So we can tell it is as metabolic acidosis. Correct, no? Then we look into HCO3 minus levels. Then we see the HCO3 minus levels. So then you look for compensation. How do we calculate compensation? This is nothing but this is decreased by 4. Normal is 24. Normal is 24. HCO3 minus is 20. So 4 into 1.25. 4 into 1.25. Correct, no? For every 1 milliequivalent decrease in HCO3 minus levels, PCO2 should decrease by 1.25. So for 4 milliequivalents, it should have decreased by 5. It should have decreased by 5. And PCO2 is 35. So it is adequately compensated. So we can call it as simple metabolic acidosis. So we can have one more example. Example number 5. Answer for this. Answer for example number 5. Okay, you are, Shravanti, you are telling metabolic alkalosis is not compensated. Why is it not compensated? Is there any other disorder as well, Shravanti, as to why this is not compensated? Yeah, good. Why? What is the secondary disorder then? Okay, we'll see. So initially, we look at the pH. pH is increased, so there is alkalemia. There is, yes, good, Devi. It is respiratory acidosis. Okay, we'll see how. since there is increase in PS, there is alkalemia. PCO2 as well is increased. It is moving in the same direction. So it is metabolic alkalemia. Alkalosis. So next we calculate for compensation. Compensation is if HCO3 minus increases by 1 milliequivalent, PCO3 minus should increase by 0.75. So when we calculate for compensation, HCO3 minus levels have increased by 6 into 0.75. That will be equal to somewhere around 4.5, somewhere around 4.5. Correct, no? Somewhere around 4.5. But PCO2 is much higher. PCO2 is much higher. If PCO2 should be higher than what is expected, then when is the PCO2 higher? When will PCO2 be higher? If there is respiratory acidosis. We saw in the initial chart, if PCO2 is high, then the reason is respiratory acidosis. So the second component over here is respiratory acidosis. Okay, good. So we are done with this. Now we saw up till compensation. This was the 3 steps we followed. We follow 3 steps. Check for acidemia or alkalemia. Then what did we do? We checked for the primary disorder. Then we saw whether the body compensated it or not. Now moving further to next steps. Okay. Then we check for something called as anion gap. So let's see what this concept of anion gap is. Okay. We'll see what the concept of anion gap is. Normally what happens is in our body, cations will be equal to anions. The number of cations will be equal to number of anions. Okay. So we see in this table, we can see in this table, if this being cations and this being anions. Okay. So cation being majorly contributed by Na plus and unmeasured cations along with very few potassium, which these unmeasured can be calcium, magnesium, proteins, etc. And anions being majorly contributed by chlorine, HCO3 minus, and unmeasured anions like phosphates, sulfates, and proteins. Okay. So with this, we can see that there will be some amount of anion gap. Why is it called anion gap? Because unmeasured anions are much more than unmeasured cations. If we differentiate unmeasured anions by unmeasured cations, we get some amount of anion gap. This is normally present in our body. So unmeasured anions is nothing but minus unmeasured cations, which is anion gap. Normally it is around 8 to 10 milliequivalents per liter. So normally this is around 8 to 10 milliequivalents per liter. Next we see unmeasured anions minus unmeasured cations. How did we arrive at this equation? How did we arrive at this equation is unmeasured cations plus Na plus will be equal to unmeasured anions plus Cl minus plus HCO3 minus. Correct, no? If we move this over here, unmeasured anions minus unmeasured cations will be equal to Na plus minus Cl minus plus HCO3 minus. So anion gap will be equal to this. That is how we arrive at this formula. So we can see anion gap is nothing but Na plus minus Cl minus plus HCO3 minus. So this is the formula using which we calculate anion gap. So how does this anion gap become important in our scenario? In ABG, how does this play a role? So if there is presence of increase in the anions, that means there is increase in pathologic acids in the body. Correct, no? Which means if there is pathologic acids, which means there will be metabolic acidosis. This metabolic acidosis is of 2 types. Normal anion gap metabolic acidosis and high anion gap metabolic acidosis. In normal anion gap metabolic acidosis, this value will be maintained. 8 to 10 milliequivalents per liter will be maintained. How it will be maintained, we see. Over here, this part is not changed. The unmeasured part doesn't change. It is the HCO3 minus level which there is loss of HCO3 minus level. Example, in case of diarrhea, colon contains a large amount of HCO3 minus levels. This is gone. This is gone out of the body. So HCO3 minus levels decrease, and this is compensated by increase in chlorine. When this happens, we see that anion gap is maintained. The normal anion gap is maintained. This anion gap and this anion gap, which was previously seen in normal condition of the body, is same. So we see that there is normal anion gap, but metabolic acidosis due to loss of HCO3 minus. So this is one entity wherein there will be loss of HCO3 minus levels and compensating increase in chlorine levels. Since there is also increase in chlorine levels, it is called as hyperchloremic metabolic acidosis. Okay, and there is one more entity which is called as high anion gap metabolic acidosis. In this, the metabolic acidosis is because of increase in this part, unmeasured anions. This contributes to pathologic acids being added in the body. When this happens, this anion gap tends to increase. See, it is increased. Over here it was this much, but over here it is this much. No? So there is the anion gap is increased because this has increased, because this unmeasured anions have increased. When this happens, there will be high anion gap metabolic acidosis. For example, when there is diabetic ketoacidosis, ketone bodies are added, which contributes to increase in the unmeasured anions. Correct? No? This is what happens. That's why it is called as high anion gap metabolic acidosis. So this was the basic concept of anion gap. And few conditions, there will be hypoalbuminemia. What happens in hypoalbuminemia is usually albumin contributes to unmeasured anion. Correct? No? So if albumin decreases, and there is metabolic acidosis, high anion gap metabolic acidosis, AGMA is there, it will show as normal itself, because unmeasured anions, there is decrease in unmeasured anions because of decrease in albumin. But after this, some amount of pathologic acids get added. So as a whole, what happens? Anion gap will become of equal. It will become of not equal. Anion gap will become of normal, because initially there was decrease in unmeasured anions because of decrease in albumin. So in order to prevent this false negative values, false low values, what we do, we get one more formula called as adjusted anion gap. So what is it? Anion gap measured plus 2.5 into 4, which is the normal level, minus the albumin level. In order to avoid false low anion gap, we use adjusted anion gap in case of hypoalbuminemia. Using this, can we solve this sum? Where were we? Example, we have answer. Okay, Pawan tells it to be respiratory acidosis. Okay. With any other answer? Reduced. How much has CO2 minus reduced? It has reduced by around, what was the compensation for every 1 milliequivalent decrease in HCO3 minus? PCO2 should decrease by 1.25. So how much it has decreased? It should have decreased by 14.4, somewhere around 14.4. But it has only decreased by 9. So there is one more component. There is metabolic acidosis plus respiratory acidosis. Since we see PCO2 is higher than the expected value, there is respiratory acidosis as well. So there is a mixed picture. Next, since there is metabolic acidosis, we calculate anion gap. Anion gap, on calculating, we see that anion gap is around 10.5. This is normal. Okay, 9. It is around 9 to 10. Okay, it is around 9 to 10. But this is a normal value. Around 8 to 12, we can consider it to be normal. So there is normal anion gap metabolic acidosis along with mild respiratory alkalosis. So normal anion gap metabolic acidosis along with mild respiratory alkalosis, correct? So next we'll go into a clinical scenario. We'll see a clinical scenario, okay? Which one we'll solve? We'll either solve 10 or 11, which is simpler. We'll solve, okay, since it includes correcting albumin as well. Solve the 11th one. Solve the 11th one. 11th question. Anyone can solve 11th answer? Over here, please note that albumin level is no. Albumin level is low. So you'll have to use the adjusted formula. Where is the formula gone? This is the adjusted. Anyone answer for this? Okay, Satya tells uncompensated metabolic acidosis. That means there is some other secondary process for it to be uncompensated. What is it? Okay, fine. Let's solve. Let's solve. See, what is the clinical scenario? 35-year-old gentleman post binge drinking alcohol was found unconscious. Okay, this is our clinical scenario. So first step, acidemia or alkalemia. pH is decreased, so there is alkalemia. What happens to PCO2? PCO2 as well as is decreased. So there is metabolic acidosis. Then we check for compensation. 1 milliequivalent of decrease in HCO3 minus should decrease PCO2 by 1.25 mmHg. Over here, it is decreased by 16 to 24 means 8. So 8 into 1.25. This will be somewhere around 10. So PCO2 should have decreased by 10. No, PCO2 is higher than the expected value. Since PCO2 is high, there is respiratory acidosis, mild respiratory acidosis as well as present. Okay, then we calculate anion gap. Yeah, good, Sanjay, good, Sanjay, good. We calculate anion gap. Na plus is 134 minus 108 plus 16. Correct, no? This will give around 12. But see, if you see this value, it seems as though anion gap is normal. It seems as though the disorder is normal anion gap metabolic acidosis. If we would have ignored this picture, of albumin, it should have seen as though it is NAGMA. But now if we use the adjusted formula, we